You've built a powerful teacher model. It's accurate, it generalizes well, and every single inference call is costing you a small fortune, so you decide to distill it into something leaner. Smart move, but here's what nobody tells you up front. The distillation process itself can burn through your compute budget just as fast as running the teacher in production, if you're not careful. In this video, I'm going to walk you through the specific strategies that actually move the needle when you're running large-scale distillation projects. Not generic advice, concrete techniques with the trade-offs you need to know before you commit. Just to set context, when I say large scale, I mean scenarios where your teacher model has 7 billion parameters or more, your distillation dataset runs into hundreds of millions of tokens, and your student training spans multiple GPU nodes over days or weeks. If you're doing a small LoRa distillation on a single A100, some of this still applies, but the ROI on these optimizations really shows up at scale. The cost drivers in distillation are the same three you always fight: teacher inference to generate soft labels, student forward and backward passes, and data throughput, reading, tokenizing, batching. Let's go through how to attack each one. The single highest leverage move most teams miss: decouple teacher inference from student training entirely. By default, many distillation pipelines run the teacher forward pass online, meaning every training step, you're paying for teacher inference on that batch. If you're doing 10 epochs, you're running the teacher 10 times on the same data. That's 9 wasted runs. Instead, run the teacher once over your entire dataset, serialize the output logits or probability distributions to disk, and load them as static training targets during student training. You've just cut your teacher compute by up to 90%. The trade-off: storage. Full logits for a large vocabulary over a big dataset can run into terabytes. You have two options here. First, vocabulary pruning. Instead of saving all 32,000 plus logits per token, save only the top K, typically the top 50 to 200. The long tail of near zero probabilities contributes almost nothing to the KL divergence loss anyway. Second, quantize the stored logits. Float 16, or even int8, is usually sufficient for training signal. You don't need float 32 precision in cached soft labels. Combined, these two tricks can reduce your logit storage by 95% or more, making this approach practical even at scale. More data is not always better in distillation. In fact, it can actively waste compute. Here's why. Your student model learns the most from examples where the teacher's output distribution is genuinely informative, meaning uncertain, nuanced, or multimodal. Examples where the teacher is 99.9% confident on a single token. Those barely move the gradients. You're spending compute for nearly zero learning signal. This is the idea behind data pruning for distillation. Before you even start student training, score your dataset by the teacher's output entropy or uncertainty. High entropy examples, where the teacher is less certain, are your most valuable training signal. Low entropy, near deterministic examples can be subsampled heavily. In practice, teams have reported cutting dataset size by 30 to 50% using this approach with minimal degradation in student quality, because the student still sees the hard cases. Run a fast single-pass entropy scoring sweep over your data before committing to the full training run. It's cheap insurance. A related technique: curriculum distillation. Start training on the easiest, most confident teacher examples, and progressively introduce the hard ones. This can improve convergence speed, letting you reach a target loss with fewer total gradient steps. Even with a perfect dataset, you can bleed money from infrastructure inefficiency. 3 things to audit immediately. First, gradient checkpointing. If you're training a large student, say 3 billion to 7 billion parameters, you're probably running into memory pressure that forces smaller batch sizes, which means more steps, which means more time. Gradient checkpointing trades a roughly 30% increase in compute for a dramatic reduction in memory, letting you run larger batches. Net cost is usually lower because fewer larger batches reduce overhead. Second, mixed precision training. If you're not running float 16 or float 16 on your student training already, you're leaving massive efficiency gains on the table. Modern H100s and A100s run tensor cores at 2 to 3 times throughput in FP16 versus FP32. There's almost no reason to train distillation targets in full precision. Third, and this one is underrated, I/O pipelining. On multi-GPU setups, your GPUs are often sitting idle waiting on data loading. Profile your training loop and check GPU utilization. If it's below 85%, your bottleneck might be your data loader, not your compute. Prefetching increasing worker count and using memory-mapped formats like Arrow or raw binary tensors instead of JSON or CSV can close that gap significantly. Feature-based distillation, matching hidden states, attention maps, or intermediate representations between teacher and student, can improve quality, but it also adds forward pass cost on the teacher side if done online, and adds loss computation overhead. If you're using feature distillation, be deliberate about which layers you match. Research consistently shows that distilling from the last quarter of the teacher's layers provides most of the benefit. Matching every single layer is expensive and often redundant. Pick 2 or 3 strategically placed layers, typically near the middle and near the output, and you'll capture most of the representational transfer at a fraction of the cost. Also worth noting, if you've cached your teacher logits already, feature-based distillation requires a separate caching pass for activations. Batch those 2 passes together in a single sweep if possible. Don't make 2 full passes through your teacher when one will do. If you're on a cloud provider, your teacher inference caching run, the one-time sweep where you generate all the soft labels, is a perfect candidate for spot or preemptible instances. It's a long, parallelizable, checkpoint-friendly job. If a node gets preempted, you just resume from your last written shard. Compare the economics. On-demand H100 on AWS is roughly $10 per GPU hour as of this recording. Spot pricing for the same instance can run 60 to 70% cheaper. For a multi-day teacher inference sweep across a cluster, that difference compounds quickly. The key is designing your inference pipeline to write output shards incrementally, with clear shard-level completion tracking, so preemptions are recoverable without recomputing entire chunks. This is not exotic engineering, it's just good checkpoint discipline. Your student training, on the other hand, is trickier to run on spot, because preemption mid-epoch with large gradient state is more disruptive. On-demand or reserved capacity makes more sense there, especially for the final training runs. One of the most common ways distillation projects waste compute is running to completion when the model converged 40% of the way through. Set up rigorous early stopping based on validation loss on a held-out slice of your distillation dataset. And separately, run lightweight downstream task evals at regular intervals. The reason you need both: validation distillation loss and actual task performance can decouple. Sometimes the student's KL divergence continues to improve, while downstream quality is already plateaued or even regressed, especially if the student is under capacity for the task. A practical setup: eval every 5% of total training steps. Keep a small but representative eval set, a few thousand examples. And track both the distillation loss and 1 or 2 task-specific metrics. The overhead is small. The potential savings from catching early convergence are large. Progressive training schedules also help. Start with a higher learning rate and decay aggressively. Fast convergence in the early phase means you can make go, no-go decisions on hyperparameters earlier before committing to full training runs. To recap the full pipeline, start by scoring your dataset with a fast entropy pass and prune the low-signal examples. Then run your teacher in a single inference sweep on spot instances, caching top K quantized logits, and if you need feature distillation, batch those activations in the same pass. Set up your student training with mixed precision, gradient checkpointing, and properly pipelined data loading. Pick your 2 or 3 layer matching targets if you're doing feature distillation. Train with early stopping and regular task evals on on-demand or reserved capacity. Done correctly, this approach typically cuts total distillation compute cost by 50 to 70% compared to a naive online setup, without meaningful quality loss. The gains are highest when your dataset is large and you were previously running the teacher redundantly across epochs. Model distillation is one of the highest leverage things you can do for production ML economics, but only if the distillation process itself isn't eating your budget. The strategies we covered today aren't speculative. They're the patterns that show up repeatedly in the engineering write-ups from teams that do this at real scale. If you want to go deeper, I'll link a few papers in the description, particularly the work on data pruning for distillation and curriculum approaches. And if you've run into a cost challenge on a distillation project I didn't cover, drop it in the comments. I read them. Like and subscribe if this was useful. and I'll see you in the next one.